Welcome to The Explainer. Today, we're going to pull back the curtain on the hidden networks that pretty much run our world, industrial control systems, or ICS. Now, these are the brains behind everything from our power grids and factories to our water supply. And as you're about to see, they play by a completely different set of rules than the internet you're using right now. Right off the bat, let's get one thing straight. The network that handles your emails and spreadsheets is not, I repeat, not the same one that keeps your lights on. You see, one is all about data and speed, the other is about physical safety and just rock-solid reliability. And mixing those two up, well, that can have some really catastrophic consequences. So that's the big question we're going to tackle today, isn't it? How exactly are they different? And more importantly, why should you care? The answers have huge implications for efficiency, for reliability, and, above all, for safety. Okay, to really get a handle on this, we first need to understand that we're talking about two totally separate worlds of networking. On one side, you've got information technology, or IT. That's the world of data, servers, and business. But on the other, you have operational technology, or OT, and that's the world of physical machines, processes, and control. And this picture, well, it just captures that OT environment perfectly. I mean, forget about quiet, air-conditioned server rooms. Think loud factory floors, scorching hot power plants, water treatment facilities. In this world, a network failure isn't just a lost email. No way. It's a production line grinding to a halt. It's physical equipment getting destroyed, or even worse, a critical safety incident. The stakes here are physical, and they are immediate. And this is where you can really see the differences stack up. Over on the IT side, you've got all the stuff you know. Business apps running on Windows or Linux. But in OT, the tech is totally purpose-built. Instead of a standard PC, you've got these rugged little boxes called PLCs, programmable logic controllers, that basically act as the dedicated brain for a specific machine. And it's all managed by something called SCADA systems, which give operators that bird's-eye view of the entire physical process. Everything, and I mean everything, is designed for one thing, controlling real-world machines with absolute split-second precision. But all this data, the commands, the sensor readings, the status updates, it has to travel on something, right? Just like cars need roads, data needs a physical highway. So let's take a look at the actual copper, light, and air that make up the backbone of these industrial networks. Before we dive into the different kinds of highways, we kind of need to know the rules of the road. And there are three really critical factors. First is bandwidth. Think of that as how many lanes the highway has, or how much data it can carry. Then there's attenuation, which is basically how much the signal fades out over a long distance. And finally, and this one is so important in these environments, is noise immunity. How well does that signal hold up against all the electrical interference you'd find on a noisy factory floor? All right, let's start with copper, the classic workhorse of networking. Now, older systems use that coaxial cable you see on the right, but modern networks mostly rely on twisted pair. And it's amazing, just the simple act of twisting the wires helps cancel out electrical interference. But in an industrial setting, they take it a step further with what's called shielded twisted pair, or STP. That extra foil shield you see? It's basically like armor, protecting that critical data from the really intense electrical noise that heavy machinery pumps out. But what if you wanted to be completely 100% immune to electrical noise? Well, then you use light. This is a fiber optic cable. It's really cool. A laser just shoots pulses of light down a super thin glass or plastic core. And because it's light, not electricity, it is totally unaffected by all that electrical chaos that can corrupt data on copper wires. And the performance is, well, it's just incredible. I mean, look at this table. A single-mode fiber can carry data for up to 100 kilometers without needing a boost. That's 62 miles. It's exactly why utilities managing massive power grids have been using it for decades. And it's not just about speed and distance, it's also unbelievably secure. You can't just tap into a fiber cable without physically breaking it, which would be detected immediately. So we've got our physical highways. But, long before modern networking came on the scene, industrial systems had their own very unique rules of the road. Let's actually take a step back in time and look at the original communication standards that were built specifically for industry. The earliest systems were built on a really simple idea: one wire, one job. Just like this diagram shows, every single sensor, every motor, had its own dedicated line running all the way back to the controller. Sure, it was incredibly reliable, no sharing, no data collisions, but you can just imagine the massive, tangled web of wires this created. It was ridiculously expensive to install and a total nightmare to maintain. It just couldn't scale up. So naturally, the standards had to evolve. We went from RS-232, which was good for those simple one-to-one links, to RS-422, which was an improvement that let one master device talk to multiple slave devices. But the real game changer was RS-485. This one allowed lots of devices to share a single line over really long distances, and it basically laid the groundwork for the huge distributed control systems we have today. And this brings us to a huge shift in industrial networking. The reliable, predictable world of serial communication was about to collide head-on with the high-speed, flexible powerhouse from the IT world. This, my friends, is the story of when Ethernet entered the factory. But here's the problem. Ethernet wasn't built for this world. It's what we call non-deterministic, which is a fancy way of saying there are absolutely no guarantees. Imagine an ambulance carrying a critical "shut down the machine now" command, but it's stuck in traffic behind a car that's just casually reporting the daily temperature. That's the Ethernet problem in a nutshell. Collisions and unpredictable delays are just not acceptable when a few milliseconds can be the difference between a safe shutdown and a total disaster. And this quote from our source material really just says it all. In an office, a half-second delay loading a web page is maybe a little annoying. But in a factory, on that OT network, it can be downright dangerous. So the key takeaway here is that in OT, timing isn't just about performance. It's about safety. It's about protecting people and expensive equipment. So you might be asking yourself, if it was so problematic, why on earth did Ethernet win? Well, the reasons were super practical. First, it was cheap. Second, IT staff already knew how to manage it. But the biggest reason was integration. It was the bridge that could finally connect the factory floor to the front office, and this integration unlocked incredible new efficiencies. But in building that bridge, it also opened a brand new door, connecting these once isolated, secure systems to the much larger and far less secure world of IT. So far, we've pretty much been focused inside the four walls of a plant. But what about systems that span entire regions or even countries? I'm talking about electrical grids, pipelines, rail networks. Let's zoom out and see how these massive systems get connected. Just take a look at this diagram. It really shows you the sheer scale of the challenge we're talking about. You've got a central control center that needs to talk to and manage remote stations that could be hundreds of miles away, and it has to happen in real time. There's no single solution for this, so engineers have to rely on a whole toolbox of different long-distance communication technologies. And what a toolbox it is. You've got everything from good old reliable telephone lines to all sorts of radio frequencies. For the absolute most remote locations, you're using satellite links. Of course, there's our high-performance friend, fiber optics. And then there's one of the cleverest solutions of all, power line carrier, which actually sends data signals over the high-voltage power lines themselves. How cool is that? And finally, it's not just what you use to connect everything, it's how you lay it all out. These different network layouts or topologies are all about balancing cost, performance, and reliability. You could have a dedicated point-to-point link for every single site, which is super reliable but also super expensive. Or you could use a multi-drop layout where a bunch of sites share one communication line to save money. It's always a trade-off. So let's recap. We've built this incredibly complex network. It has specialized devices running on a mix of copper and fiber, using a mashup of legacy and modern protocols, all connected over vast distances by radio, satellite, and phone lines. Which brings us to our final and maybe the most important question for today. With all of these physical and logical layers of connection, where in the world do the vulnerabilities lie?